Okay, so let's continue with looking at finite differences for advection, diffusion. So let me talk a little bit about diffusion. So say if we have this equation, and we wanted to discretize this term. We already saw that, right? So finite difference method. Let me just put using Taylor because it's Taylor series, but truncated it's Taylor polynomials. You think of it as you wish. So I told you I was going to mention today about thinking of the PDE evaluated in the middle of the grid. It's simple, but let's do it because maybe it's the first time you see it. So let's do it. So here is let's do a forward and a backward Taylor series. Dot. Okay, the parenthesis is the same guy that's above, okay? So save time. Now, if I have this, this is equal to okay, this is simple. This is just what we already saw, right? Forward, backward, you add this up, you kill this guy, you kill this guy, right? And we get what we need. Then, so we saw this. This was explicit. So let me make a sharper division. So this was now we have the implicit, which is the Crank-Nicholson. Okay, and Crank-Nicholson is, now for, this was just for the diffusion term was this. Excuse me. Okay, can I write it like this to save time? Okay, this is the same as this, but at time n instead of time n plus 1. Okay, this is just, is this okay? Right, it's just this stencil, but this is wrong here, sorry. Right, sorry, this is wrong. So this is the same thing here, but at time at time n. Okay, so this reminds us of the trapezoid rule, right? Which is basically the right-hand side, the x-axis, right? Written, so it's like the x-axis. It's like approximating uxx at n plus 1 plus uxx at n and divide by 2. But quotes and quotes just to, right? So it's simple. So this is Crank-Nicholson. Okay, so what I want to show you is that, let me write here. Let me maybe do it like this. We can interpret as the scheme centered at time n plus a half. Okay, so it's like the PDE, the heat equation. So, right, it's like the heat equation. So it's going to be like this. Let me put it like this here. Evaluate it at this point. Okay, so let's double check this. It's a good exercise. It's simple, very simple, but it's a good exercise. So therefore, I'm going to do the same thing I did before, Taylor-Series expansion. Now in time, forward and backward. But here I have something wrong, yes. Just like this to remind us. Hope I have this right. Right, okay. So the 4 came out because it's delta t over 2. Okay. So now I can write from here, I can write this. Okay, so this is kind of looks just very simple, just a matter of interpretation, checking where we look at things. The problem is that I have to write, my arm gets tired because I have to write all these Taylor expansions. So I did the same thing as there, but now in time. So here I'm expanding forward in time, backward in time, okay? And then this that looked like our explicit Euler, right, which was first order, if you have it centered at this point, which is actually not on our grid, we're going to have to deal with that in just a second, right? And there's these tricks. Sometimes there's people that use, for example, I might mention it sometime, not very much, like staggered grid. Sometimes the grid's like this, then shifted like this, shifted by half. So you take advantage, try to kill terms in the Taylor series. So here, I subtract this guy and this guy, I get this, which looks like our forward Euler, which was first order. But here, because it's centered, at this time, it's second order. It's not that I almost said it looks like a second order. No, it is second order, right? Because then when I added this, right, this is what I got. Here, I did not kill it. I added, so I got this guy, the delta t, and so on. Okay? Because here, this guy here, I can also think of it, this average of the trapezoidal rule, which for the ODE, I saw the trapezoidal rule as the trapezoidal rule for integration of the ODE written in integral form. No big deal. Now the trapezoidal rule here for Crank-Nicholson can think of an average of 2 times, right? So this guy can also be thought as being at time n plus a half. So, okay, so we get this. And now there's something very simple. Okay, let me show you. So this is, let's look at the spatial time again. The spatial, I mean, not time, spatial differentiation again. Look what I'm going to do now. Very simple, but it's good for us to also always be prepared to sometimes get this kind of interpretation. So let me stop talking. Also do this wrong. So I'm assuming actually smoothness, right? So I can expand all these guys. Look, no big deal, right? So what I'm assuming is that C is smooth, of course, and this function here, which is a second derivative of C, can be expanded in the Taylor series. What's the big deal? In time, the second spatial derivative can be as a function. Just forget about it. Call it f. Can be expanded in time. For that, forward in time, here it is. Boom. Okay. I can also do it backward. So wait a minute, you guys got to correct me, right? This is forward in time, this is backward. Let me see if I got this right, yeah. Yeah, this is backward in time. Yeah, forward, right? I had the signs wrong. So can you see what I'm getting at? Sum, right? So if I sum these guys, I kill this, and actually I can say that the average of this guy, right, divided by 2 is equal to this guy up to order delta x, delta t squared. So it's second order. So therefore, what we're doing is like this. Let me put a picture here from the notes. Okay, so this is a J. Okay, so basically, I am evaluating I'm using, this is my molecule for Crank-Nicholson. Right, but I'm evaluating the PDE here at j n plus a half, but I'm only using, right, this method here. I'm only using the points, right? I mean, the points on the grid, okay? So actually, on the notes, I have a drawing of the wrong molecule for the Crank-Nicholson. Okay, well, the explicit, yeah, I'm talking, this is the wrong molecule. Okay, so note in the grid that I forgot to put the ones, of course, these 3 points here, no, these 3 points here at n plus 1. So the molecule there is right. I don't know. Okay, so these are tricks to kill terms in the thing, and sometimes you can think that you're evaluating the PDE, sometimes here in the middle, right? But only using grid points. Okay, so for those of you, we call this a quick review . Right, so those of you who saw this, who did PDEs with me last semester, saw this. So for those of you who did not, but doing PDEs now, whatever, might have already seen this, but let's just do, it's a very quick review, just to call your attention of things that, if you know, excellent. If you don't know, or you don't remember, right, refresh your memory. So if we have a system like this, right? Well, I have to say, well, A, B are real matrices. Let me say, well, M by M. U, F are vectors. And I'm going to say that actually, for now, these are constant matrices, okay? So by saying that, I'm thinking about, in terms of PDEs, of a linear constant coefficient PDE, right? Note that these matrices could not be constant. They could vary in space or in time, which then, if this is a wave problem, for example, this would be a variable coefficient PDE, which means, for example, the propagation speed of a wave changes in space or in time. In many of the problems I work, they change in space because it's a heterogeneous medium, a medium that, for example, the ocean with different depths. I'm going to give you an example in a while. So the different depth gives you a different wave speed, right? So the matrix could change. So there are many situations. The matrix also could depend on U, which then would be a quasi-linear system, which looks a little bit like Burger's equation, right? The speed depends on the solution, right? So we can think of that. No big deal. Okay, so we say that this system, okay, let's see, some of, who knows this? I mean, well, here there's Lucas and Erica that saw this with me. So when can I say that this system is hyperbolic? What does it mean this system is hyperbolic? Yes, so the eigenvalues of A are real, right? Which means we have real valued propagation speeds, okay? So that's what I'm going to write. So I mean, for those of you who haven't seen the full course of the PDEs, whatever, as I said, you can take PDE here at IMPA, PDEs and applications after you take this course, and hopefully you get a big appetite to learn more theory. If you have done PDEs and applications before this course, you have a big appetite now to see it on the computer and how to construct approximate solutions for difficult problems. So the order doesn't really matter, right? So I know that. So, okay. So this system is said to be hyperbolic, okay, in opposition to elliptic, like Laplace equation, in opposition to parabolic, which is heat equation. Okay, it's hyperbolic if the matrix A, and I'll show you in just a second why is that, is, let me abbreviate like this, diagonalizable with real eigenvalues, okay? So it actually is called strictly hyperbolic if lambda I is different from lambda j, that is distinct eigenvalues, because then it is diagonalizable, right? If they're real valuable, and it has to be hyperbolic if you have repeated eigenvalues, right? But you have the complete base of eigenvectors. Okay, no big deal. So if I use if P minus 1A P is equal to lambda, okay, like this, and I set V equal to inverse P, which is the modal matrix, that is the matrix with the eigenvectors, right? So, and for simplicity for now, with B equal to 0, F equal to 0, just for simplicity, kill this guy, just remove it for the time being, then Vt equals to this. Well, actually, in the notes I didn't put V equal to 0, so let me put it like this. Let me leave it like this. Yeah, I'm going to say F equal to 0 in just a second, but let's leave it like that. I can still tell the story I want to tell. So do you see what I've done? I mean, all of this is very simple. Is that I have a linear system of equations, okay, because A does not depend on U. But if I can do this even for a variable coefficient, sometimes I'm going to show examples where actually I can have a variable coefficient, which means a matrix that is not constant. But if it's always diagonalizable, I can do this. And this is basically here, it's a change of variables, right? This is just a change of variables that diagonalizes my system. If F is equal to 0 for the time being, this means that all modes decouple, right? V1, so basically this means that I have this equation here in parallel. So I have, if this is like a wave equation, I have M unidirectional wave equations that don't talk to each other. The problem is linear. At the end, I can solve for each mode. And at the end, I do the change of variables to come back to u. And I have the solution. So when I come back to u, all the modes then get entangled, say in the colloquial sense of entangled, and gives you the solution. So intuitively, what does this mean? Intuitively, this means that in the system, right, and you kind of know this, if I have a certain number of real eigenvalues which are positive, and a certain number of eigenvalues which are negative, that means that I have modes that propagate to the right in this coordinate system independently at different speeds. The speed is what? Is the eigenvalue. Okay? And I have a certain number of modes that propagate to the left with the different speeds, which are the eigenvalues which are negative, real negative, right? And at the end, depending on my initial condition, blah, 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 when I go back, right? It's so easy to solve this. When I go back to my original variables u, I have a solution which has a complicated traffic of information. Some guys going to the right, some guys going to the left, and that might depend on the initial condition of, like, I can have a system. I'm going to mention this to you. That I can have a system. We see this in the PDEs course that, for example, has a positive eigenvalue and a negative eigenvalue. But I can put an initial condition that only triggers the right-going eigenvalue, which means the left-going mode, which is like a channel. If we think of a table where I control channels to the right and channels left, where the channel to the left is switched off. I don't need to switch it on because the initial condition only has a wave going to the right. Okay? Intuitive, right? So here I have M, quote-unquote, channels, where depending on my initial condition, channels in the sense a little bit of like a sound table, okay? Even though this does not have to be a sound wave. But it's good to think like that because we have this intuition of a sound table, right? So I can have a condition, initial condition that just have something going to the left, nothing to the right, and so and so, okay? So this is very good. And then, but the important thing for us here, numerically speaking, and we saw eigenvalues for ODEs and eigenvalues for region of stability, blah, 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 is that here, if I'm using an upwind, okay, so now let's think of this. Okay, good question for you. And I'll drink a little water as I'm talking, so my voice. Suppose I only have right-going eigenvalues. Okay, all the eigenvalues are positive. Okay, I have a 3-by-3 system, 3 real value positive eigenvalues. I tell you, solve this problem using, the question is very simple, using upwind. What is the delta t you're going to use? The delta x and delta t you're going to use? Yes, you're going to use, you said it right. So what you're going to do is you have, looking at this, you have, say, you could think of 3 different courant numbers, right? One for each wave equation as we saw. And you have to be conservative. You're going to use the one that makes all 3 cases stable, right? So that's what you have to do with the updating. So sometimes also you might have situations of a little bit like a stiffness, right? You might not even have the fastest propagating mode, which therefore you gotta make a small delta t, right? But or also things will blow up. So exactly, okay? So if you have a problem with a separation of scales in terms of propagation speeds, okay, that's the idea. So that's the reason to show this, is that then you see that, right? You have the way, if you have an explicit method with conditional stability, you gotta take care of this, okay? And another picture which is of interest too, almost forgot to write, is that if I think, right, I show this in the PDEs course. So if I have a point here, xt, in my initial data, right? I'll talk more about this. This is how the information goes to that point. Does this graph make sense to you? Look, from the method of characteristics, right here I'm thinking as lambda constant. So therefore this is a straight line. So this is a little bit what I think the characteristics as channels, in a sort of informal sense, channels, almost like little wires where information propagates, right? And over these lines, in this case here, V is constant. VI is constant over each I line, right? Line 1, line 2, line 3. And this is how the information from the initial data will propagate to this point in space and time, right? Through the method of characteristics. When B is non-zero, then all these guys are coupled, right? Because I'm going to have a B term here, right? And the B term there's no way I can uncouple the modes. It would sort of mix the modes already in this coordinate system, the coordinate system of, say, that diagonalizes the matrix. Okay, but no big deal. Sometimes that's what you can do. That's what you have. But the good thing, even if you have the B here, the good thing is that if you can actually write things, diagonalize your system, whatever, if it's not too big, because it's on, here you have control of the speeds, so you have control of which discretization, delta x, delta t, you're going to choose. Right? It's much easier to see it here than to see it here. You agree? Right? To see the stepping. Okay, and you can check, for example, if you want, there's a comment here in the notes, you can check if you want, depending on the sign of B, right? Just put here a plus or a minus BV, right? And you will see that in some cases, depending on the sign of B, you can see that through the dispersion relation, for example. If B is a damping term, or it puts energy inside. It will depend on the sign, right? Okay. Okay, let's see what are the comments I want to make. Yeah, let me make a minor comment here, because then I'll give you examples of problems, of concrete problems, right, that has a situation like this, that, look, if I have a situation like this, right, we see that this is this A coefficient, which would be a scalar analog of this, just so we can discuss, okay? If this would be a scalar analog of this, or if I put, even I could also write here a lambda, doesn't matter, right? Let me leave it. The notes is like this, but because I got it from here and there, so I put lambda. This means I have a speed, which just depends on space and time. So sometimes there's a medium that's changing, right? I'm going to draw some application, right? Some application for water waves, which is my area of research, main area of research. This guy here could be changing because the speed depends on the depth of the water. So then it depends on x. And there are some really complicated problems which I don't work in right now, but I mean, which is time-dependent bottoms. That could happen. A time-dependent bottom could happen in many ways. One that's very sort of complicated, this one I've never worked, which is like a transport. If the bottom is made out of sand, we see it here in the beach, the depth varies in time, right? Because sand is being carried. Sometimes these models also are used for a bottom changing time, for example, when there's a tsunami, that's because of a submarine earthquake. So the depth suddenly changes, goes up and down, up or down, right? So models would use that. So when you have this, okay, then you have a characteristic that depends, an ODE that depends on at each point depends on time, right? This coefficient is more complicated. So this orbit of the characteristic will not be a straight line, but still is okay. Remember when I mentioned last class the semi-Lagrangian method, I said, look, for each time step, you can approximate it by a straight line, but that if the curve is smooth and not varying too fast, that's okay. It's a straight line here, then a straight line here, then a straight line there, right? So this is no big deal, but we have to know what to do in what situation, and knowing all the slippery parts, the dangerous parts of our choices, right? And it's okay to deal with dangerous parts, because then the method will be more efficient if you say, okay, it's unstable in this case, but that's not the case I have. So one thing which is very important in this course is knowing the theory so that you can make choices, right? And in many things, in particular numerical methods, the choice is the short blanket choice, right? You have to know if you want to cover your feet or cover your head or in between, yeah? But that's fun, right? Or else we would just use packages for our lives. And as applied mathematicians, not always, I mean, most of the time, I never use packages. We write our own codes to understand the math, the PDE aspect, and the related physical aspect. And both together are very interesting, right? Okay. So, okay, the two examples. So I'm skipping one part, but I think it's a repetition of here. So examples of, two examples of the PDEs course I mentioned about this example, but let me share it with you. Sometimes Z is upwards, sometimes it's not. So let me explain what are these guys. So P is pressure. Here is speed of at that point. 1 over kappa of Z is called compressibility. I'll tell you just in a second what it is. Rho of Z. Density, let's see what else I have to say. Speed, or let me say velocity, doesn't mean it. At ZT, and the same thing for pressure. And it's okay, so let me tell, and then I'll say more. So this is a problem for acoustic waves, a very simple problem, or model, but good. For acoustic waves in the crust of the Earth. So it's a 1D, okay, acoustic problem for in the crust of the Earth. You know, it's if it's constant coefficients, it's exactly what I said there. So if kappa is constant and rho is constant, this can be written like this, right? So let me say PU right? This can be written like this, obviously. And we can find the eigenvalues of the matrix, okay, which is the propagation speed. So I don't even have it written here, but it would be like, I think it's square root of rho over kappa. You can check it. So let me explain the model. So the model, which is a simplified model, but actually the 2D version of it is already very complicated and can be used to understand things for acoustic waves in the crust of the Earth related, for example, one is oil exploration. So this model is called a layered model. One D, right? Because it's one dimension. Sometimes Z points upwards, sometimes it points downwards. That's not a big deal. So here we have layers of different material, just like in the crust of the Earth, right? You can see some pictures. One place where this is so beautiful and obvious, like you see photos of Grand Canyon, right, in Arizona. But many places you see this. So here, for example, I have a layer of one material, another one, say sand, rock, blah, 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 and it goes, okay? So this problem is a layered problem. You can put your initial data as a pressure wave. That's how it's done, a pressure wave on, here is the surface of the Earth, right? So you have a person here. This is the surface of the Earth. And this data could be different data, could be even like a delta one when sometimes you explode something or you hit something very fast, doesn't matter. So you have a pressure wave that's going to travel down. The relative scale of the pressure wave with the scale of the variations are very important for the mathematics that can be done, okay? I'm not going to get into this. But if you want to solve this problem numerically, right, just a few, you're going to have modes initially coming down, but say as soon as the wave sees these interfaces, right, there's going to be a reflection because it's a change of speed. So using the jargon, which is appropriate for acoustic waves, and this jargon, I use it in general, we use it in water waves, the reflected wave is a little bit like an echo, right? I say something, whoop, part of my voice passes, part of my voice comes back, which is transmitted and reflected wave. So if I want to solve this problem, and I'm not going to get too much detail now, but I need to solve this, I have that the propagation speed is piecewise constant, right? This guy's right. But this problem here you can check. It's very easy to check. It's hyperbolic, strictly hyperbolic, right? So the eigenvalues are real always, and they are plus or minus. No, I'm not even going to write it. I mean, just check it. It's very simple. Which means that in each layer, I can have a wave propagating down with a speed, certain speed, which is the acoustic speed, and a wave propagating up with the same value, right? But the thing that it changes from layer to layer, right? And solving this problem analytically is not easy, right? You can do some of the problem, but it's not easy. And numerically, care is need to be taken, but it's also not super complicated. Okay, so here's an example. So I'll leave it at this for now. And here, let's see what else I want to say. Okay, and then if I have another example, is water waves in the regime which is called long waves or shallow water. Why is this? Because depth over length is small. Okay, so this is the regime where depth, and in this regime, in the fluids course, some of you had done the fluids course, we can deduce this linear shallow water equation. No, this is not linear. This is the nonlinear. Sorry, even better. Right. And let me. Okay, so this is called the shallow water model. Shallow water model because the water is small. The water depth is small compared to the wavelength. Okay, and this is actually. Where this is very small, actually, you have taken, in the PDEs course, you see this, you have taken the limit to 0, doesn't matter. And the wave, if it's a pulse, this would be the wavelength. If it's periodic, it's a period. So this is very small compared to this, so this is very big compared to that. So this is, for example, the case of a tsunami, right? In a tsunami, the depth is 4,000 meters. I think I mentioned this before. I don't know, not in this class. So the depth is 4,000 meters. That looks like very deep. No, but it's a shallow water regime because the tsunami sometimes could be 50 to 100 kilometers long. So therefore, you're in the long wave regime, shallow water regime. And this system here is hyperbolic, okay? And you can easily write it in this fashion where now the matrix for this guy is going to depend on eta, which is the wave elevation from the undisturbed level, okay? And on u, which is the speed of the particles. Just like here, here's the speed of the particles. So pay attention, I almost forgot, that there's two speeds to pay attention here. So think of this, if I jump on top of a bunch of matrices, which have a certain different compressibility, okay? A mattress is very hard, the other one is very soft. So if I jump, I put 5 matrices, one on top of the other, and I jump on top of the mattress, there's going to be a compression wave that's going to propagate down. It's like putting different springs, one on top of the other, right? So therefore, when the spring goes like this, like that, there's the speed of this part of the spring going up and down. That's the u. But there's the other speed, which is of this compression wave propagating down through the matrices, here through the layers, okay? The eigenvalues are related to the wave speed, this propagation of the compression wave. And this u is the speed at which a particle here in the spring goes up and down, okay? Got the difference? The same thing here in an analogous way, okay? And there's actually a wave problem. I mentioned this in the other course I gave that I've already solved. Was actually not exactly like this, would almost go back to my thesis, which is a wave over a bottom like this. And why I was solving this? Well, this is where the bottom of the ocean is piecewise constant, but different. But because my advisor had some theory for this problem, and we wanted to bring theories from the acoustic problem to the water wave problem. And here, look at this. Oh, I have to say the shallow water speed, so the eigenvalues are going to be plus or minus the square root of GH. Okay? So here actually G does not appear. So anyway, this is bad. So this is the dimensionless equation. Okay? In the dimensional one, sorry, this is bad, because I wasn't thinking of talking about this. So in the dimensional case, you see here there's no gravity here. It's because we have scaled the problem. It's dimensionless. And that's what these parameters alpha appear. But in the dimensional problem, we have that the propagation speeds are going to be square root of GH. Here it's going to be, here the propagation speeds are going to be plus or minus 1, because I have normalized the problem. Are you okay with that? Sorry, but I'm trying to put more information. So here, square root of GH. So if I have a problem like this with variable depth, you see that over each of these regions, the propagation speed is constant. So this problem has a mathematical analogy with this one. Propagation speed is constant, right? And the idea, say the things that went back to days a little bit after my thesis and so on, was to import mathematical technology. There were some theorems when these layers were random, which means random speed, very complicated theorems. How to then bring those theorems that had worked here to here. But one cool thing is that here, the acoustic problem is naturally linear. It's okay to be linear. And for water waves, you can add many things. You can add dispersion, which you already know, but this problem has no dispersion. And you can add nonlinearity, which is this parameter alpha here. Look, it's the parameter that multiplies all the nonlinear terms. Okay? So what is nice, and I leave it to you, is that if you write this equation in this form, so let me maybe use this space here. Okay? For this problem, A is not constant anymore. A depends on the solution, because this equation is quasi-linear. It's a little bit like Burger's equation. But it's very easy to check. Just rewrite this in this form, okay? And you will see that this problem always has two distinct real eigenvalues. So it's strictly hyperbolic. It has two wave speeds, but now the wave speed is more complicated. It depends on the solution. Is that a mystery for you? No. Burger's equation had the same. Okay? So, and you can actually rewrite the system. In the PDEs course, we see this, not here. You can, using Riemann invariance and so on, you can rewrite the system in a way that it looks like a Burger's equation one way and the other way. But this is not important here, just cultural information. Don't worry if you don't know it, okay? So, okay, so but the important thing is that here you have the eigenvalues, which are the wave speeds, and sometimes you can more or less estimate and know more or less what to do in terms of choosing the propagation speed, okay? So here in the notes, maybe let me be complete, okay? So for this system here, look. Look, if I write this is good. I just saw I was going to change pages. So it's very easy. It's super, super easy, right? Anybody can do this. Rewrite the system like this. Find the eigenvalues of A. Here they are. No surprise. The eigenvalues depend on the solution. And look at this. The system is hyperbolic. The eigenvalues are real. They're distinct, okay? And if I make the nonlinearity, alpha is the nonlinearity parameter. If I make the system linear, what are the eigenvalues? Plus or minus 1. Because this is a dimensionless system, has been normalized, and the speeds are plus 1, minus 1. So the characteristics are like this, right? There are modes going with speed 1 this way, or modes going with speed 1 that way. But then, when nonlinearity comes in, the speeds can change. Okay? The speeds can change. All right? And I can have maybe a positive and a negative eigenvalue. Okay? Or maybe even I can have two of the same sign. Okay. Okay. Okay, good. I have some time. I'll continue. And good, because I think I'll finish today. Another quick review of PDEs, but it's good to set our minds for numerical methods, and in particular, set our minds for the famous, CFL condition, Courant-Friedrichs-Levy condition. So let me continue with a quick, easy review of PDEs. Now let's take what we learned as an undergraduate as the wave equation, right? Usually if one talks about the wave equation, we would think about this, but in numerics and so on, sometimes I would ask, oh, wait a minute, are you talking about the second order wave equation or the unidirectional wave equation, right? Because the unidirectional wave equation is very useful for us to test many things because it's very simple. Okay, so here, the characteristics are like this, right? It's not difficult to see. Also, you can see that this operator can be written like this. Okay, so basically you already see that there's like two unidirectional wave equations kind of mixed together. Okay, and therefore we know that the characteristics are going to be something, say, can make like this maybe. Blue going that way, and red going that way, okay? Okay, and LU can be rewritten as this, which is in the coordinate systems of the characteristics, okay? It looks like an ODE. Why does it look like an ODE? Because I can write it like this. So at first, this I call V. It's an ODE in eta. I integrate, get a constant of integration. So here in the notes, I'm not going to do it in detail here. I do it in the PDEs course. And then I integrate the other guy, right? You can do this by separation of variables and so on. And this will tell us that UXT is equal to a right-going wave plus a left-going wave. Okay, I forgot to put here. Whoops, let me erase here. And I forgot to put here that we need initial conditions. Two initial conditions because of second order. Okay, these are the initial conditions. And then if we integrate this, we get the famous D'Alembert's solution. Let's see if I got it right. Yes, 2C. Yeah. Okay, this is D'Alembert's solution, which is great because we can, right, solve this analytically. Right, this problem usually appears in our lives as the problem of the vibrating string, right? I think you've seen this. But this is D'Alembert's solution, okay, which means, so who of you have seen this done this way? Let me see. Raise your hands. Okay, everybody basically, yeah. Excellent. So, right, we learn separation of variables, blah, blah. Here, we can use the characteristics to integrate this twice. You get this. And this is very nice. This is very nice. First, because it tells us this. Look, if we think of the vibrating string or a wave, right, in an interval, and say you just pull this up like this, okay, like a vibrating string. You just pull it and you let it go. If you pull it and you let it go, this will vibrate like that. But it's actually interesting to see that in this case, G is 0 because the initial speed is 0. This guy doesn't appear. And what we have when we see the string just going up and down is a perfect synchronization of a right and the left going wave, right? A right and a left going wave of half the amplitude. So if I have, for example, a very big domain and for the water waves, and I put just a hump of water in the middle, which I mean is this. Now I'm talking about something like this. Right? And I abandon it there, this hump of water, what will happen? So suppose this is a Gaussian, because we use, in numerics, it's very good, very useful to use a Gaussian, as I suggested to you, because it's a smooth, it's infinity wave-like function that in Fourier, it's also a Gaussian, so it's very easy for us to picture things. Anyway, but here you don't have to think Fourier. So if I put this Gaussian here, a bunch of water, like for example, generated by an earthquake, right? But we don't have the earthquake. We just see this water like this, and you let it go. What will happen? Half of the wave goes to the right. A copy of the wave, half goes to the right, half goes to the left. Okay? Good. Now, let me erase this so I can use the space. Now let's look at two things of this problem, which are very important. So the first thing I want to ask is this. If I put a point here, I'm using the notation just called xt. Sometimes I put capital X, capital T. And I want to know what is the domain of dependence of this guy, which means if I change my initial data, will this guy know? Maybe yes, maybe no. Because the information comes like that, right? Which would be this and this, okay? And therefore, because the solution at this point has this expression, it depends on F at the extreme points, but it depends on G. Look at the interior. Okay, so this is the domain of dependence. And then we also have the region of influence. Okay, and okay, we see this very simple from the formula, right? So this point will affect, And how do we see this? Because you get any point here, you check the domain of dependence, and that guy is inside the domain of dependence, log is portion. Then the region of influence is this sort of cone, right? Okay, great. Now, the importance of showing this is great. It's first to refresh our memory with respect to these things. But as we will see later on in terms of CFL condition, but we already saw this with a current number, is that there is a relation in terms of the domain of dependence of the PDE and sort of the domain of dependence of the numerical problem. Okay? And I think you can already relate to what I'm going to say now, is that the domain of dependence of the numerical problem and the CFL condition comes with that. We're not going to prove the CFL condition, but a good intuition is that it has to contain, the numerical one has to contain the exact one, and not the other way around. Okay? And not the other way around. So that's why it's good for us to refresh our memories of what is domain of dependence, region of influence, and the D'Alembert solution gives us a very clear indication of that. Okay, I have a few minutes. So let me mention, I'm going to basically mention things we already saw for ODs, and then I'll finish and leave an example for next class. An example of something that I mentioned already to you, which is what if I'm in the upwind situation, but I decide to use a method which is downwind, sort of going against the flow, right? We'll see what happens. Okay, so to wrap things up, well, now we're going to talk a little bit about convergence, and for a time being, consistency. Then we'll talk about stability. Convergence and consistency. So convergence, usually, let me put it this way, translating here in Portuguese, we want UJN to approximate U xj Tn and that the approximation improves as delta x, delta t go down to 0, right? So in our notation of the notes, I'm going to use, okay, so for those who want to follow, also have a text, I'm going to, for a while, I'm going to follow the book by Strickwerda, okay, that we have here in the library and was suggested to you. So notation, then my notation switches a little bit here and there because I'm following Strickwerda. So Strickwerda, at some point, he writes the PD like this. I don't know why he writes, well, he writes xt, doesn't matter. First order nt, and where this p in his notation is a polynomial, so that's no big deal, just so we can exercise that. And where the hypothesis, right, was solution is fully determined by initial data. And this is a linear PDE. So then we're going to repeat a little bit things we saw before, but let's repeat it in strict Veda's words. The definition. So given the PDE. Now, so we get also use two other notations. Okay, so the script calligraphic L is just a differential operator. So given the PDE and a difference operator, which he writes LU equal to F L writes like this, just an operator that depends on the grid. We say that the difference scheme is consistent with the PDE if for any smooth function phi of Tx okay, so I'm just exercising different words with you so that you feel comfortable, but no novelty, right? We already know this, no big deal. Right? Just we get used to different notation, right? No big deal, which is we saw the consistency before looking at a local truncation error, and I called your attention that consistency has to do with sort of operators being close together in some sense, looking one more like the other. Stability is solutions, right? Next class, I don't have time, I'm going to basically finish here. Next class, it's solutions not allowing them to divert out of control, right? That's stability. And there's super theorems that then say that consistency plus stability equals convergence, which means equivalence, right? So here's just new notation, calligraphic L differential operator, L difference operator, and this, instead of talking to the solution, instead of talking about, not talking to the solution, talking about, we cannot talk to a solution, right? Talking about the solution of the differential equations, it's basically the same. Here he's saying get. It's the same in the sense of operators. Here it makes clear, very clear that operators nearby. Just get a smooth function, hit it with a differential operator, hit it with a difference operator. So a jargon we're going to use from spectral methods, Trefethen's book, another book, soon is also when you say a grid function. What is a grid function? A grid function is usually you get a vector by applying a function on a grid, right? So this is more or less what's happening here. And this goes to 0 as these guys go, that's consistency. So it's just basically to call you the attention, but no big deal. That consistency came before with a solution of an ODE, which did not solve the difference equation. There was a residual which was a local truncation error, and that went to 0. Here we could also talk about a residual, if this was a solution of this, whatever, but it doesn't matter. But this is good also, that's why I showed you, because here it calls even more our attention, because who knows who is phi? Any guy with a smoothness. I hit it with one operator, I hit it with the other operator, and they're getting closer and closer to doing the same thing. Right? I can see in your faces, no surprise. This is a slightly different way of showing the same thing. Okay? So we'll come back next class, next Monday, and continue on this. Okay? Thank you.